Sometimes they go on either side of the line. Do the H2O with the water? No, I don't. Oh, you know what? Did I tell you what the first step is to do after you do the split the half reactions? Balance everything but what? Oxygen. Everything but oxygen. Balance everything.
Okay, so on the last one, you said that the last set is the
Yes. Reduction occurs in the cathode. Okay, ready? Who wants more time? I need more time. All right, more time. So I guess we can identify the half reactions, which is kind of a hard part here, huh? Okay, yeah. You don't have to add anything. I mean, the acidic means you just do other ones.
Oh, okay. So you always do something and
When it says basic, after you're done doing everything like normal, then you can change it. All right, look at this. Oxygen's balanced. I just have to add two H2s here, sorry, two H pluses here. And then what? Two electrons over here. This one, we need to put a 2 in front of this. All right? Who got tricked by that? We didn't do it. All right, not bad. We'll forgive you. So now we add waters. Which side needs water? For none of them? Hydrogens. 2 H pluses over here. And then I guess the 2 electrons over here, huh? That's nice. So what? H2O2 combining with carbon dioxides to form carboxylic acid and oxygen gas. Okay. What is the anode? H2O2? Because it's going from what to what?
From -4 to 0.
Okay, -2. Oxidation state of that oxygen to 0. Alright, there's 2 of them, so it contributes to -4, but it's just the -2. Now that's important because in the future, we're going to be asked how many electrons transfer this process.
how much is it?
Oh, this one here? Well, there's a couple ways. There's a couple ways to remember this. One is that the sum of all the oxidation numbers on the element has to be the charge on the compound. True? So what's the charge on the compound? Nothing. So whatever the oxidation number is for oxygen, it has to add up to 0.
Because like this diatomic and oxygen is not like -2, then it's 0.
What? Well, we would, I mean, it usually would be -2, right? But if we put this as -2, that would be -4, but there's no charge here. Well, I lied. The real reason is, anytime anything's elemental, it's always 0.
Okay.
But like this, we kind of forget that rule, because we've said that rule before, and it didn't stick. And so we have some other rule to help us. And I think this is pretty obvious. Whatever it is, if I multiply by 2, it equals 0. Whatever the oxidation number is there, right? You see that? No? Because the oxidation number here, whatever it is for oxygen, there's 2 of them. So that oxidation number plus whatever the other oxidation number is for the second oxygen, which it should be the same thing because it's the same thing, then the answer should be 0. So we're looking at some value in this universe, x, the same value, times 2, or x plus x equals 0. Any ideas? Negative 2? Negative 2 plus a negative 2? No, that's a negative 4. It's got to be 0, right? It's got to be 0. So, that's one way to remember the fact that elements by themselves are always 0. Here's another one, right? So, what's the oxidation number on rubidium? Yeah, right, it's got to be 0 because the sum of whatever it is adds up to 0 because there's no charge on this thing, right?
So then, why do we have the charges here that we know?
Those are anionic compounds, right? So if I say rubidium oxide, for example, right? Now, the oxidation number here is -2, this one is a +1, right?
Okay.
Question?
Is it right to assume that aqueous have charge?
Aqueous, things that are aqueous?
Yeah, and then ones that are not aqueous doesn't have charge.
So, I don't know. I'm not sure if I understand the scope of the question. But like that, for example. Is that okay? This is aqueous. Oh, you mean there's no charge here? Yeah. So there doesn't need to be a charge on something that's aqueous. Yeah. But in general, it'll generally be charged. Or so. I mean, I don't know. Depends on how they write the equation, right? So we can write this. You'll see this, right? NaCl aqueous. But we know it's really talking about sodium ions and chloride ions separate from each other. So I don't know how helpful that generalization will be and what it actually might tell us. Okay. So we went from -2. Oh no, yeah. Oxidation state number 2 to 0. So that was oxidation or reduction?
That was oxidation.
Oxidation. The value, was it getting smaller, a -2 all the way up to a 0? Was it getting smaller? No. Getting bigger. Oxidation. Hydrogen peroxide is our cathode or anode? What's that?
So you can't say that it's a negative.
No.
So that's the anode.
That's the anode. Very good.
And then reaction.
The anode reaction is it being oxidized to oxygen gas. Right? That's our half reaction here. Right? So they didn't call it the anode this time because this is a liquid, right? It's not a solid metallic or it's not solid.
So is that's a proper terminology then, when it's a liquid?
Yeah. I mean, for this to be occurring at some surface, you'd have to have some surface, and that would technically be whatever the anode is, like a platinum wire or something. This would be the anode reaction. All right, praise the day. We're moving forward. Now, this is a bit archaic, and I'm not thrilled about trying to get you guys to learn this, but one run through and a little bit of a general recognition, recognizing it once will be helpful. All right, now. So this little method for writing a chemical reaction, displaying it, right? Over here we can see copper going to 2-, silver ions going to silver solid, and then we have these two lines in between representing a salt. Okay? All right, so we're not going to be practicing this. Now, in batteries, or electrochemical cells, right, which is the same as a battery, or battery is an example of an electrochemical cell, you have voltages. Voltages. Do you guys know how much a double A voltage is? Close.
2.
Closer. Close. 1.5. 1.5. And now they vary, in fact, because they're made of different materials. The cheaper ones are usually 1.2 or something like that. But in general, nowadays it's getting more common, that are more ubiquitous. All of them are 1.5 volts. Double A. How about a triple A? It's 1.5 as well. How about the C? You guys ever seen a C battery or a D battery?
Those little disc ones?
No, those are big fat ones that go on old flashlights.
Oh, yeah.
Yeah,
Big round ones.
something like that. So, all of these are cells that produce or provide 1.5 volts. 1.5 volts.
Why are they different voltages then?
Well,
That lasts longer because the amps are different.
yes, the amount of current that they want to provide can differ. And if they're requiring the same amount of current, then they will last longer because there's more material. So, when I was doing my postdoc at the University of Hawaii, in Manoa, our work was funded by the Central Intelligence Agency, and they were interested in us developing a power source that was significantly smaller. Because if you had these little listening devices, right, that you would, leave somewhere, right, if you're in the other country's embassy or something like that, and you just want to drop something on the ground, right, and it's going to record sound for a day or something like that, or a year, right? The recording device is really, really small, but the power to power it is significantly large. It's large enough that you can see it. The recording device itself is so small that you can see that's the way. But the power source, the battery, was too large. You can say, what's that? Why is there a battery? What's going on here? Right? So they were interested in trying to make something smaller, but you can't get a smaller battery and then have enough power to do so. Right? Because batteries' power is dependent on their size. So we were working on fuel cells, and we weren't really in the miniaturization part, but what we were doing is, because a fuel cell can be really, really tiny, because it doesn't store its fuel with it, right? The reactants can be collected from wherever they're at, in the air, or maybe you stick it up against a tree that sucks in the glucose, or maybe plug it into people, right? And burn the glucose in their blood, right? Something like that. Then the fuel cell itself wouldn't have to be very big. It would just have the glucose constantly kind of flowing by. Just take advantage of it. There's another thing that people were interested in this for powering things like pacemakers. Anybody ever dealt with a pacemaker to any significant extent and want to admit it? You did. So the batteries last how long? Anybody know? 3 years? I thought it was like 10 years. But they're pretty long. Pretty long. But, just to have an operation to change your pacemaker can be worth trying to find a way maybe you never have to have an operation just to change your pacemaker. Right? So, yeah, they're interested in that sort of thing. Another thing that they're interested in is the type of device that would do two things. One, get power from sugar levels, and two, from the amount of power that's being generated, it would be able to determine what the sugar level is. And then, if it could determine what the sugar level was, it could determine whether it had to inject you with a little bit of insulin. Not necessarily in yourself, right, from the outside, but from something on the inside. Right? So instead of you having to do it, sugar in your blood. Anyways, a couple of applications for really small power sources like fuel cells. So, voltage is our way of measuring the amount of energy, joules, over coulombs. Coulombs. Now, a coulomb is our measure, or our unit for charge. Our unit for charge. Okay? And you don't have to get too involved with understanding what a coulomb is or love it or anything like that. It's really basically just an amount of charge associated with a number of electrons. Okay, so we get tables of what we call standard reduction potentials, or E naught, RAD meaning reduction potentials. Okay, so a table of reduction potentials are going to look like which one of these, top or bottom? Bottom, where it's some sort of chemical reaction with electrons going in to the reactant, right? So this is an example of a reductive half reaction, right? And then associated with that is going to be some sort of a voltage, or the energy associated with that process. Okay? So let's look at this table of reductive half reactions. Can you see that okay? See okay, right? A little small, but all of them are reductive half reactions. No oxidations there. But you can pick a couple of them and determine whether or not you can make, or how much voltage you would get if you made a battery out of it. Right? Now, if I have this one near the bottom here, aluminum ions taking electrons and forming aluminum metal, that negative 1.66 is not a favorable reaction. So voltages, they lucked out or unlucky for us. Positive values are an indication of a favorable reaction.
What happens in major reactions?
Well, if you want them to occur, you have to push them. And that's what we do when we charge a battery, right? Push the current the other way. So let's make a battery. Let's make a battery out of aluminum and cadmium. Aluminum and cadmium, okay? Now, it's up to you to combine aluminum with cadmium in such a way that you get a positive voltage, all right? You don't want a battery that won't work. You want to have something that works. Okay, so you're going to take aluminum, you're going to take the aluminum half reaction, the reductive half reaction, the cadmium reductive half reaction. Find a way, one of them's going to have to flip around, right? You can't put two reductive half reactions, one's going to have to flip. So that the electron can actually end up going on something else. Right? Does that make sense? And then tell me what the resulting voltage is between the aluminum and, or make a aluminum cadmium